Section 3.3 discusses writing functions, and it has a lot to do with finding patterns and writing an algebraic rule for that pattern. So look at example 1. We're going to use a table to write a function. And it says, suppose Tasha babysits and charges $5 per hour. So there's a table here that shows the number of hours that Tasha has worked and the amount of money that she earned. So if she works 1 hour, she gets $5. 2 hours, $10. 3 hours, $15, and 4 hours, $20. And so the amount of money Tasha earns is 5 times the number of hours she works. So for every hour that she works, 1 times $5 is 5. 2 times $5, because that's how much she earns per hour, is 10. 3 times 5 is 15. 4 times 5 is 20. So Tasha earns 5 times the number of hours she works. If you write an equation using 2 different variables to show this relationship, it would look like y, which we're going to use for the amount of money that she earned, because that's what it says here. So the amount of money that she earns is determined by taking $5 per hour and multiplying it to the number of hours that she worked. And I used x because we labeled x here as the number of hours that she worked. So y equals 5x is the relationship between time worked and the amount of money that she earns. And you can see that down here that we wrote it out using our words. This is what it looks like. So, next slide. Example 2. You need to determine a relationship between the x and y values and write an equation. So this one doesn't have a story to it. As x increases by 1, notice that y is increasing by 1 as well. So you want to list all the possible relationships between the first x and y value. So what do we do to x to get to this y value? What do we do to this x to get to this y value? What do we do to this x to get to this y value? And you want to do the same thing to every x to get to that new y value. So at this point, stop the video and see if you can figure out what we're doing to x to get to y. Alright, so if you need a little hint, we already talked about this, but notice that this pattern of increasing by 1 each time is usually part of your rule. And this happens to be a linear relationship that's in the form of y equals mx plus b. So whenever you see this constant difference right here in y, it's going to either be m or b. You'll soon learn that it becomes m, the coefficient of x. So that means that we're going to take x, whatever this value is here, multiply it by 1, and then that would give us 1. And how would we go from 1 to negative 2? Well, we're going backwards, or we're reducing the number by 3. So if we took 1 and subtracted 3, we'd get negative 2. 2 times 1 is 2, minus 3 is negative 1. 3 times 1 is 3, minus 3 is 0. 4 times 1 is 4, minus 3 is 1. So, step 2 says determine if one relationship works for the remaining values. That's pretty much what we just did. And then, oh, it didn't tell us to do it, but we're going to actually write our rule. So y equals, if our m is 1, we're just going to write an x. And then we subtracted 3 each time. So this is our function rule. Take x, multiply it by 1, and subtract 3. Now this is your turn. You're going to determine the relationship between the x and y values in this list of ordered pairs. So it's not written as a table this time, but you do see that your x is increasing by 1, 1, 2, 3, 4. Notice what's happening to y, 3, 6, 9, 12. Look at the common difference between 3 and 6, 6 and 9 and 12, and use what we've just learned in the previous example to help write your function rule. So turn the video off at this point and try to do step 1 and step 2 on your own. Okay, so we noticed that there was a common difference between the y's, and the y's are increasing by 3. And so the possible relationships, if it happens to be, now not everything is linear, but if it happens to be linear in the form of y equals mx plus b, we might want to try that first. Because as x is increasing by 1, y is increasing by 3. We learned in the previous example that common difference oftentimes becomes m. So maybe if we multiply x by 3, this common difference that we see here, from here to here we're adding 3, from here to here we're adding 3, and from here to here we're adding 3. So we're going to let that become x. So y, or the m, so y equals 3x. And then let's see what else we have to do to x to get to our y. So if I take 1 and multiply it by 3, I get 3. What do I have to do to get to the y? Nothing. So then for the next one, 2 times 3 is 6. There you go. I don't have to add or subtract anything. 3 times 3 is 9, and 4 times 3 is 12. So it appears that this function rule works for all 4 ordered pairs. Now in this slide, we're identifying independent and dependent variables, and we've done a lot of talking about independent and dependent variables. Essentially, you have to look to see between two things that are being compared, which thing drives the other thing, or which thing affects the other thing. Independent variables, the input value of a function, so that's our x value, so you might want to put up here that that's the x value. It's a variable whose value drives the value of the output or the dependent variable. So your dependent variable is your output of a function, which is your y. And it is a variable whose value depends on the value of the input. So we already talked about Tasha. The amount of money she earns depends on, or is a function of, the amount of time she works. Excuse me. So because the amount of money she earns depends on the amount of time she works, wow, I'm having a real tough time talking, then that means the amount of money that she earns is the dependent variable, and I just wrote that in the wrong color. This is the dependent variable, and then time is our independent variable. 9 times out of 10, time is going to be your independent variable because we can never affect time. We can't slow time down, we can't speed it up. I mean, how many hours I work is how my paycheck is determined. So I'm not told you're only getting $500, so therefore you can only work, 20 hours or whatever it happens to be. Typically, it's based upon the hours that you work. So let's look at example 1. In the winter, more electricity is used when the temperature goes down, and less is used when the temperature rises. So you want to ask yourself what things are being compared. So we're comparing electricity used and temperature. So determine what drives what. Does the electricity used determine what the temperature is outside, or does the temperature outside determine how much electricity is used? And I think you all agree that the temperature outside drives or affects how much electricity is used. So that means that our temperature is our independent variable, whereas our electricity used is our dependent variable. And then that's been spelled out for you here. Example 2. You determined this on your own, so stop the video, ask yourself what drives what. You've got the cost of shipping a package is based on its weight, so you're comparing cost of shipping and weight. So stop the video and figure out which is dependent and which is independent. So you're asking yourself, does cost affect weight, or does the weight affect the cost? Definitely the weight of a package affects the cost of shipping that package. So that means that the weight is your independent variable. And the cost of shipping is going to be your dependent variable. So same thing for example 3. I want you to stop the video and you determine what affects what drives what. Okay, we've got the faster Ron walks, the quicker he gets home. So we're comparing Ron's speed for walking versus the time it takes him to get home. So as Ron's speed increases, or I guess I should ask it this way, does Ron's speed affect how quickly he gets home, or does how quickly he gets home affect his speed? The speed actually is driving the time. The quicker he walks, the quicker he gets home. The slower he walks, the slower he gets home. So speed actually is what's affecting the time. So if we want to really look at independent, faster Ron walks, which is speed, is the independent variable. You can determine what speed you want to go. So you have the control over the speed. And then even though, and this is where that odd one is, even though quicker he gets home is time, and I said 9 times out of 10, time is your independent, in this case, you have control over the speed. Do I want to go fast today or do I want to go slow today? And that's going to affect how quickly it takes you to get home. So the quicker he gets home is your independent variable. I'm sorry, your dependent variable. All right, so we've been talking a lot about a function rule. It's an algebraic expression that defines a function, and so we did a lot of function rules in slope-intercept form. Y equals mx plus b. That's not the only way that you can write a function rule, but this is one that we talked about a lot today. Then we're going to move into function notation. So instead of using this y here, we're going to use f of x. Y and f of x are the same thing. It's just a different way of writing a function rule. And essentially it's calling this rule right here, it's labeling it as f. It's saying that we're going to call this rule f. They like to call things rule f or rule g or rule h. F, g, and h tend to be the most popular names of functions. And it's read f of x because we're going to take this function rule right here and we're going to replace this x with some number. So if x is the independent variable and y is the dependent variable, then the function notation for y is f of x, and it's read, as we said, f of x, where f names the function. So that name of that function can change. It can be g of x, it can be h of x. So if we're going to go back to talking about Tasha, remember Tasha's earnings were y equals 5x. So we're just going to replace y with f of x. And so now it's read f of x is equal to 5x. We just exchanged the y for f of x. For the following examples, you're going to identify the independent and the dependent variables, and you're going to write an equation in function notation for each situation. So instead of writing y equals, you're going to write f of x equals. So example 1, a lawyer's fee is $20 per hour. So that's important, $20 per hour for her services. So we're comparing the fee for the lawyer versus the number of hours she works. So the question you ask yourself, does her fee depend upon the number of hours she works, or does the number of hours she works depends upon her fee? So the fee for the lawyer is $20 per hour, but that's how much she charges per hour, but her total fee is how much she's earned. So we're going to let H represent the number of hours that the lawyer works, and as you look at this, the fee for the lawyer depends on how many hours she works. Because if she works 1 hour, she gets $200. That's her total fee. If she works 2 hours, she gets $400 as her total fee. If she works 3 hours, she gets $600. So however many hours she works will drive what her fee is. So the fee is dependent. So the dependent variable is the fee, and that's total fee. Whereas the independent variable is the number of hours worked. And so we're going to let H represent that number of hours that she works. So instead of X, we're using H for that independent variable. And so the function rule for the lawyer's fees would be, we're going to do F of, instead of X, we're going to do F of H equals, and then up here was important. All I did for every hour that she worked was multiply it to 200. 1 hour times 200 is 200. 2 hours times 200 was 400. 3 hours times 200 was 600. So however many hours, which is H, we're going to multiply it to 200. So F of H is equal to 200 times H. So example 2, the administration fee to a local carnival is $8. That's like your admission fee is $8. And then each ride costs $1.50. So you have to look at this as it's not the administration fee versus the cost of the ride, it's your total cost of going to the carnival. So my total cost is being compared to what would drive my total cost? The number of rides. Because I could pay admission of $8, which is their administration fee, and ride no rides, and it would cost me $8. I could pay my admission fee and ride one ride, and that would cost me $1.50 for the one ride plus the $8, which is $9.50. I'll do it one more time. I pay my $8 admission, I ride 2 rides. So I'd multiply 2 rides to the $1.50, which gives me $3, and add the $8, which is going to give me $11 total cost. So your total cost depends on the number of rides ridden plus that $8. So what is your independent variable? Your independent variable is your number of rides. Your dependent variable is total cost. So we're going to let R represent the number of rides, and then total cost is going to be F of R, because that's our Y, that's our output. So if this is R, independent variable, the dependent variable is going to be F of R. So the function rule for the total cost of the carnival is F of R is equal to the number of rides ridden, so times $1.50, so we have $1.50 times the number of rides ridden, which is R, plus that $8 admission fee. Then we come to evaluating functions. So here you've been given a function rule, f of x is equal to 5x, and they want you to find what is f of x when x is 6 and when x is 7.5. So we're just going to take 6 and plug it in for x. So here's how you write it. So for the first one, we're going to find f of 6. So the function rule is 5x, so I'm going to do 5 parentheses. Instead of the x, I'm going to replace it with parentheses, and I'm going to plug 6 in to wherever I have parentheses, or in other words, wherever there's an x. So 5 times 6 is 30. So when x is 6, my output f of x is 30. So for the second one, instead of plugging in 6, this time we're plugging in 7.5. So we're going to put 7.5 in for x, and I've got 5 parentheses, and we're putting in 7.5. So we're going to multiply 5 to 7.5. So I get 37.5. So when x is 7.5, the output f of x is 37.5. So we could actually write ordered pairs to this. So you would have 6, 30 would be an ordered pair, an input and an output, and 7.5, 37.5. So an input and an output can give us an ordered pair. So you try example 2. So stop the video, put in your input and output, follow the rule, and then turn the video back on and check. Alright, so the first one you did g of 2, we're letting t be 2, and the rule is 2.3 times t, so our t is 2, and then plus 10. So 2.3 times 2 is 4.6 plus 10 gives us 14.6. The second one is g of negative 5. So be careful with your negatives. You've got 2.3 times negative 5 plus 10. So 2.3 times negative 5, excuse me, so that should be negative 11.5 plus 10 equals negative 1.5. And so again, you could have ordered pairs of 2, 14.6, and negative 5, negative 1.5. And then this last example, you are going to, well, for this section, you're going to stop the video, plug in your input values of 12 and negative 8, and then start the video and check your answers. So for the first one, you have h of 12 equals 1/2 times, instead of, oh, and they've got an h here. That's interesting. They have an h or a t here instead of an x. So let's just make it easier on ourselves and change that to an x. So I'm going to put 12 in for x. So half of 12 is 6, minus 3 is 3. So our ordered pair would be 12, 3. When x is 12, f of, or in this case, h of x is 3. So then your second input is going to be negative 8. So I replace x with negative 8. So half of negative 8 is negative 4 minus 3 equals, and this is negative 4 plus a negative 3, which would be negative 7. When x is negative 8, h of x is negative 7. Then finding the reasonable domain and range of a function. So Manuel has already sold $20 worth of tickets to the school play. He has 4 tickets left to sell at $2.50 per ticket. Write a function to describe how much money Manuel can collect from selling tickets. Find the reasonable domain and range for the function. So let's start with a function rule. Let's just call it f of x. So let's figure out what drives the function, what's our independent dependent variable. So he's already sold $20 and each ticket is $2.50 and he's got 4 tickets left to sell. So if he's got $2.50, to figure out that, first of all, f of x is going to be the total amount of money that he's collecting for the school play. Well, he's already sold $20. I'm going to take $20 and then add $2.50 per ticket. We're going to let x be the number of tickets. So our dependent variable is going to be number of tickets, which is going to be x. I'm sorry, that's our independent. Whoopsie poops. So let's change that to independent, because the number of tickets is what's determining how much money the school is going to get. And then total, let me call it dependent first. So our dependent variable is going to equal total money collected. Okay, so we've written our function rule, and let's come up with a reasonable domain and range. So our domain, D, since he only has 4 tickets left to sell, and you can't sell a portion of a ticket, that means he could sell 1 more ticket, 2 more tickets, 3 more tickets, or 4 more tickets. And a reasonable range would be plugging these values into the rule. So if we plug 1 into here, 1 times 250 is 250 plus 20. So that would give us 2250. If we plug 2 into here, 2 times 250 is $5 plus 20. So that would give us a total amount of $25. Plug 3 into here, 3 times 250 is $7.50 plus 20 is going to give us $27.50. And finally, plugging 4 into here, 4 times 250 is going to be $10 plus the $20 is going to be $30. So there's our reasonable domain and our reasonable range.